All right, welcome to the Plaid special. As usual, we're gonna try to solve some coding challenge under 40 minutes. So hopefully this stream is for entertainment purposes only. And without further ado, let's jump and see what we've got today. So, picking the random problem, pick one. All right, medium one, jump game. Uh-huh. You're given a zero-index binary string, zero-indexed binary string s, and two integers, minJump and maxJump. At the beginning, you're standing at index 0, which is equal to 0. We can move from I to j in the following condition if the following conditions are fulfilled. I plus minJump is less than j and is less than minimum between either maxJump or the end of the string. So why binary is important? I didn't get it. All right. So I can move to the next one if I plus minJump is equal to it. So if I have enough to jump to it. So if it's basically in between the current position plus minJump and the current position plus it at the end of the something or the maxJump, and I can only jump on zeros, not on ones. Return true if you can reach index s in s or false otherwise. All right, so we have 0, 1, 1, 0, 1, 0, minJump 2. All right, so here plus 2 is 2 and 3. So yes, I can jump from first 0 here to the second 0 here, and again from here to here, so it's true. Okay, length of the binary string is at least 2 elements, and minJump can be equal to maxJump, and the minimum one can be 1 and the maximum one can be the entire length of the array, not including the first element, obviously. So all right. So let's switch to the whiteboard to see if there is anything so I have a feeling it's possible to do linear time. So let's just see how. Let's get a random example. Let's say mean jump is 2, max is what, 4, or let's say 3, right? Oh, let's say 2 as well. So the problem is when I jump, or let's say the minimum is 2, then 1, 2, okay, it's 3, right? So it's 1, 2, 3, yeah, exactly. So I can jump to this element, but the minimum is 2. Oh, all right, so the minimum is 1, let's say, right? So with these settings, I can jump here only from this element, right? But the problem is the minimum is 1, right? So the minimum is 1, so I can then jump just to the next one. And from the beginning, I can jump either to 2 or to 3. Oh, okay, in this case it doesn't matter. So right, let's do this one then and say this is 2 minimum, right? So this is the only way how I can reach it, right? And we already know if we do this in reverse, the 3 is not feasible, so we can reach this one directly from here, right? And we can reach so we're already here, but from this guy we have option of going here, right? And here, all right, so let's or maybe 1, 0. So now from this guy we can go here or here, right? Or whatever is in between these min and max jump, which can be many, so there are many potential jumps. But does it? Yeah, I don't know. So basically we can form a graph of zeros, right? So we can say, okay, this 0 can be connected. So the minimum is 2, so 1, 2, the maximum is 3, so in this case it's only 1, so it can be connected to this guy. From this guy now can be connected to either 1, 2, or 3. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So the 0 can be connected only to 3, but then the 3 can be connected to 5, 0, and 6. The 5 with the minimum 1 can be connected to so not 6. And really we don't care. If you already process number 5, we technically don't care, right? All right, so this sounds like a plan. So we do the queue, the regular queue, start with 0, right? And then between I plus min, so we have these neighbors 4, and this guy and this guy, we add elements to the queue, right? If the element has been already processed, we don't do anything. If the element is the last element, we return true. Alright, so let's for search then. Why not? Let's go. So switching back to the default scene. So we need something to track the indexes that we have visited. All right. We can just have the vector of bool visited. Obviously, it's s.length. And obviously it's false by default. I guess it will be false anyway. So then we have q of int, right? So whatever. Q, we can call it Q. And the beginning we say, is it push back? Push back. I know that in sort is for something, and for something is push back. Let me check. QCPP. Okay, examples. Example. Push and pop. No, it's just push. Push and pop. All right. So push, obviously 0, that's where we start, right? Start with 0. Now while Q empty, not, we do this, we say int I equal Q top, I guess, or Q front, sorry. Top is for prior to Q front, and then Q pop. Then add next hops, which is 4 in J equals to I plus minJump, right? Nope. minJump and J less or equal to, all right, that's how it is. It's I plus minJ, that's where it starts, and then it's mean between, yeah, basically this. Right, so so we can hit the last element, and that's okay. And then we say J plus plus. So if we end it, we return false. If I equals s.length minus 1, right? Run, we return true. And for next hops, we need to also mark visited, right? So once we pop it, we say visited I true, mark I visited. So and our goal is to make sure that whatever pops up from the queue is always the valid point, so we can stay there. So we say if J equals 0 and visited and it's not visited, then we say Q push J, right? That's it. That's the whole algorithm. Space here. All right. So that's been it. Let's check if it works, I guess. No matching function to go me. Yeah, I know. Let's better say this. In target equal to s.length minus 1. Anyway, it's too long, so. And now we'll be able to do so. Begin length is technically size t, not integer, right? So we cannot equal to target, then we return, right? Run the code. Seems like it works. But too slow. Interesting. So we never visit edges that were not visited before. And yet we still, so it smells like dynamic programming, right? So if you reverse the string, so we can tell if we can reach some specific cell if any of the cells are zeros in some specific range prior to this element, right? If so, we say yes. If not, we don't know. Wait a second. First of all, let's pop. And let's do it here, right? Maybe it will help us save something. Visited 0 true. All right. And then here, which is not visited, we push it to the queue and mark J, visited J equals to true. So for the next element, we want run it. Still works. Yeah, I doubt it was. It's just one extra hop, so it won't save us. Interesting. So we visit every element exactly once, and yet it's still not fast enough. Interesting. So we add to the queue only if it's not visited, right? And we mark it visited instantly once we push it to the queue. So next time, whatever element happens that was already visited, we skip it. We don't do anything. All right, let's just see, just for point, see out v at I equal I. Yeah, there are no duplicates. Why the heck this doesn't pass? I see. So I guess the reason is that's one of the tests. This is more like a star, so we want to prioritize the element. Do we maybe want depth of search? More like style. Alright, so let's see if there are any hints, because I'm kind of curious. It's linear time with respect to s, and it seems like it's not enough. So whether it's breadth first search, and hey, we did breadth first search, but it's still not enough. Whoa. Yeah, I don't see any repeated element in the queue, right? So all elements in the queue, we do not repeat them. But obviously it's done to have all the zeros. Breadth for search n times max jump minus min jump. It's not max minus min, it's just n. We do not visit already visited nodes, it's stupid. Or n time and space is two-pointer optimization Java. C++ simple clean breadth for search solution. Okay, I just clue this why doesn't work. It's q previous whatever 0. Right, so it's front and then it's pop, and if it's length then we return true, right? So that's what that's exactly what I have written this part, right? So then I is max between I so why we try previous. So there is some optimizations going on. So A max jump and it's length -1, obviously. And yes, if it's already there. But we want the maximum between the previous and this thing passes. and the previous is the minimum Interesting. So visited is kind of useless, but having such greedy extra step, technically, I mean, my is still linear, right? But this adds extra greedy stuff to the algorithm, so it's easy to track. So if we like behind the previous, it doesn't make any difference for us to have a step back, right? All right, let me add this part. God damn it, it's not fair. I mean, it's so the algorithm works. It doesn't pass time complexity because there is a catch that you can add a little bit extra greedy stuff to it, like a star sort of thing, so to try to keep closer to the destination, which will help you equals 0. Alright, so then we say max between I plus minJump and previous, and here we say there's like a 4 and previous is the max, right, between what? Or is it the min? And I guess this thing, right? Let's see if it passes now. But this is, I mean, this is so stupid. This is so stupid. So it's not like, okay, so it's not like we actually improving the actual complexity of the algorithm. We just add some greediness to it. So asymptotically still linear, but for some specific corner case that we're testing, it gives us a little bit of speed up, just enough to pass the time complexity check. Yeah, I mean, I'm disappointed with this one, so I don't like it. It's totally dislike. Edge case is too frustrating to solve. So let's submit a few more times to see if any better solutions can be obtained here. So I wonder if I remove visited, will it be faster? So we will definitely save on memory. Because these people didn't have it, right, in the example, so it's just basically the full copy of what was in the logs. Yeah, looks like it doesn't affect on anything. Because I got 60, now it's 84, now it's 100. Memory is actually increased, so let's return it back then, and it doesn't really matter. This guarantees that we visit every node exactly once, which means every element in the string, which means is actually not even n, is number of zeros in the string. Right. Submit. Oh, really? Submit. All right. Seems like the first version was the fastest one. But I don't know if I can get to the first version. Memory is great, 48, time is not so, is 88. Okay, one loss. Maybe a couple more. And yes, okay, I will stop here. This is basically what we've got at the beginning. Alright, so despite this tiny heuristic hint, we've looked at the discussion, the rest or so. But this one again, doesn't change anything. But yes, it adds this thing. So you saw this time limit example, we have a bunch of zeros, and obviously it doesn't make sense to go through all of them. Just find the last one. Man. Frustrating, whatever. Let's switch to the whiteboard. So we have 62 for the time, 40, I would say 7, doesn't really matter, 46, 47 for space, and all together combined is 109. Oops. All right. Thanks everyone. See you next time. Bye.